Namaste. Welcome to another episode of Akashvata. Today we'll be continuing with our launch vehicle series, season 1, episode 2, where we'll be talking about the augmented satellite launch vehicle of ISRO. In the concluding remarks of the earlier episode, where I explicitly went into detail as to how ASLV-3 helped ISRO to develop its next satellite launch vehicle, and it paved the way for the development of future generation of launch vehicles. And continuation to that, today we'll be talking about SLV's big brother or ASLV-3's big brother, that is augmented satellite launch vehicles. So there is a bit of confusion as to what ASLV stands for. I and majority of the people do believe that ASLV stands for augmented satellite launch vehicles. But few people among my friends were saying that it stands for some other thing which I'm not particularly interested as to advanced satellite launch vehicle. But for me it has been augmented satellite launch vehicle and I'm going to stick with it. So moving on, I was talking about how important and pivotal the development of ASLV-3 was for our Indian launch vehicle ecosystem. When we talk about ASLV-3, we have to say this with absolute certainty that ASLV-3 paved and played a critical role in technology development, technological know-how, project management when it comes to it, and certainly acted as a critical learning experience for our scientists. Despite the success of ASLV-3, one of the areas that it was falling behind was its payload capacity. We know by this now from last week's episode that the payload capacity of ASLV-3 was limited to 40 kilograms. And it has to be said that it was quite inadequate, particularly for the time period. During this same time period, scientific satellites that were being launched by other space agencies around the world were weighing around 130 to 150 kgs. These were scientific satellites that were designed to carry out specific scientific experiments in space, and ASLV-3 was just not in the league to carry that type of scientific payloads. Now, that doesn't come as a surprise to us. And since ISRO was pursuing scientific missions, it needed a satellite vehicle that can carry a payload of that magnitude. Hence, the ASLV-3 was retired and the ASLV mission was envisaged. After conducting extensive studies, it was decided that adding two side boosters or strap-ons, we call them now, to the ASLV core stage could achieve a class of vehicle that can easily carry payloads in the magnitude of 150 kilograms. During this period, the thinking was that we should be using technologies that we have developed already and have been proven and battle tested, and the launch vehicle should be of reasonable cost, and the schedule for realization of the said vehicle should be of short time period. The reason was that when ASLV-3 was being developed, we talked about the realization plan or the realization period for ASLV-3 was 5 years. But in the end, it took 7 years for the vehicle to be developed. The entire program took 7 years. So they wanted a vehicle that they can design and construct in a short period of time, and that too at a reasonable cost. And during this phase, it was also identified that ASLV would be used as a baseline vehicle for proving some of the technologies that were required for ISRO, or particularly required of ISRO for future generation launch vehicles. And internally, ISRO intended to use this launcher for space science and space application missions. With all these parameters in mind, ASLV was considered or configured with two key guidelines. One, to maximally utilize SLV3 systems to retain the heritage of the past. Number two, to develop and quantify technologies in the areas of strap-on boosters, closed loop guidance systems, heat shield technology, and the most important of all, the vertical integration of the vehicle itself, which was required of ISRO for the future launch vehicle programs. So these were the two guidelines or parameters that they had in mind when they were envisaging or configuring the internals and externals of ASLV. So the objectives were simple. It had to be cheap, it had to be built in a short period of time, and it has to use many of existing technologies that were developed for ASLV. They just have to incorporate them into SLV into ASLV. So during this stage, it was also decided that ASLV will be a 5-stage rocket with all the stages having solid propulsion. And it was also given that it would have a gross lift capacity of 41.8 tons and its overall height or length would be 23.8 meters, considerably taller and heavier than SLV-3. So when I was doing research for this article or this audio series, what caught my attention was the nozzle shape and position of nozzle on the side boosters, that is the strap-on boosters. The design specifically asked for the two strap-on boosters have their nozzles canted at 9 degrees. So when I did a little bit digging into it, this cantation at 9 degrees was done. If cantation is the right word, forgive me, but they were canted at 9 degrees. This was done so that maximum thrust vector is attained, which in turn ensure the energetics in the lower stage propellants is increased exponentially. So they were trying to get the maximum out of whatever they had. So bang for the buck kind of a deal here. Maybe you might have known about this, but in regards to ASLV nozzle degree or cantation, and sincerely I was not aware of this and I'm glad that I know about it now. In addition to this, both third and fourth stage motors were modified and the vehicle was loaded with high energy fuel with codename HEF-20. Certain processes and certain improvements were also made to obtain a close performance tolerance of the strap-ons themselves, that is the strap-on boosters. Additionally, a bigger heat shield was also adopted to accommodate the largest size of the payloads. And in addition to all of the physical design changes, various internal systems also got a critical upgrade. Internal systems such as vehicle electronics were upgraded, control systems were also upgraded, guidance systems got an extensive rework and upgrade to work with the new vehicle itself. It has to be understood that though ASLV borrowed many of its traits from SLV3, it was complicated. The vehicle itself was complicated and the technology that they tried to incorporate into it was also complicated. Now, the 5 stages of the vehicle demanded the going right of more events and the dynamic pressure experienced by the vehicle at the end of the booster stage burn was rather high. This was high in the sense that the extreme pressure that was being exerted on the vehicle was much higher than what we were used to see in the SLV vehicle, that is the SLV3 vehicle. So the maximum dynamic pressure was substantially higher than the SLV in the ASLV. What made this particular vehicle complicated were events like burnout of the strap-ons, ignition of the core first stage, separation of the set strap-ons after their initial work is done, and particularly transfer of control to the first stage had to happen sequentially and with precise timing, meaning within close intervals of each other. So everything and every action is of critical and paramount importance. To give you a little idea of as to what I am talking about, let me run through what improvements were made to the electronics of the vehicle to achieve this meted goal of or intended goal of carrying a heavy payload. The vehicle consisted of telemetry. The telemetry system was used to monitor the in-flight performance parameters covering all stages from liftoff to satellite injection or separation. It also had tracking, it also had telecommand. Now, the telecommand system is very important because it is the abort system of the vehicle itself. Because the telecommand system was for destroying the vehicle in case of any unacceptable deviation from the normal trajectory. It also had instrumentation. Instrumentation included sensors that are used to monitor the health and flight parameters of the vehicle during the liftoff. In addition to all of this, power and control electronics are to name a few. So these were all the new additions and improved additions that were added to this vehicle. We knew that ASLV employed an open loop guidance up until the first stage was separated. And from the second stage onwards, or particularly from the ignition of the second stage itself, till the third stage separation occurred, instead of an open loop guidance system, a closed loop guidance system was added. This step was particularly done because the closed loop guidance system was to compute the velocity to be gained at every instant to achieve the angular momentum to the specified parameters. And also, a stabilized internal navigation system was added to the existing vehicle. This was done in addition to multiple redundant systems that were built into the vehicle so that the success rate of the vehicle goes up and the safety of the vehicle increases. All this were done to ensure to increase the success of the mission at the end of the day. They were acting as fail-safe systems. These were just a few of the technologies that we had to develop indigenously and deploy them in the vehicle just to achieve our target of placing heavier payloads in the low Earth orbit. These are the reasons why this particular mission was very complicated when compared to that of the SLV3 technology, because it demanded a lot of management of events that had to be executed in a flawless way, because everything has to be executed at a precise point of time and at a precise place that was predetermined in the trajectory, and the altitude of the vehicle also played an important role in the flight itself. Everything had to take place at a predetermined setting, and when timing is involved, everything has to happen at the predetermined time. And if one of those events fail, the knock-on event that is going to have on the following subsequent events is nothing but a sort of disastrous, because it is at this point of time the vehicle will be lost along with its payload. So a critical failure and a mission failure at the end. So that's a mission failed, right? If something goes wrong, either you are going to abort it, or the vehicle is going to get destroyed, or it is going to get splashed down in the Bay of Bengal. Though it looks easy in terms of borrowing certain proven technologies from SLV, and the thought that we are just going to simply scale it up to ASLV, here is where the devil lies in. As the saying goes, the devil lies in the detail. It is always and almost never easy to scale up and or scale down technologies that are developed to carry out specialist tasks. What do I mean by it? It's simply that it's always a challenge when one wants to either scale up or scale down hardware and technology, particularly in rocketry, that is rocket technology. So before we go ahead, If you are really interested, please let me know in the comments if you want me to do a detailed and complete analysis of the ASLV vehicle itself. That is, if you want me to do an exploded view version of ASLV, like where I'll be discussing the configuration of its auxiliary systems, the materials that were used, the propulsion technology that was employed or deployed or integrated, and my area of interest, avionic systems and control systems, and all the other nitty-gritty stuff of the launch vehicle itself. Please let me know in the comments. Depending on the response, I will definitely be making a very detailed video and an in-depth analysis of the internal function and engineering of ASLV vehicle itself. Moving on, let us get back on the track itself, that is the launch vehicle. So during the launch phase of this vehicle, it is of paramount importance. So you have understood what were the complications involved in it. Now let us get into the launch track record of this vehicle. So with the design completed and the vehicle taking shape, its final shape as such, the first flight of ASLV was conducted in the March of 1987. It was duly dubbed as ASLV D1, which ended in failure as the first stage ignition did not take place. As far as the reason why the first stage ignition did not take place, the reason could not be ascertained at first, but after due time and due investigation, it was attributed to the failure of the ignition chain in the it was attributed to the failure of the ignition chain in the flight environment. The very next year, after incorporating much needed changes that added reliability and redundancy to the ignition chain itself, which was the cause of the failure of the first flight, the second flight of ASLV, that is D2, took place in July of 1988. Again, this flight also ended in failure due to a structural breakup of the vehicle itself. Simply put, the vehicle disintegrated because of tremendous dynamic pressures on the vehicle itself. So there were structural issues. Mind you, internally we can think of something, but if the structure itself is fragile, then the whole vehicle is in danger, including the payload. So when a detailed investigation was done, we in the sense that ISRO discovered a major design shortcoming, such as inadequate control during the transition from the strap-on to the first stage control and in the design of the autopilot that was employed or used in the launch vehicle. This was like adding cherry on top of the cake. Like, you know that there is some structural issues in the vehicle itself. The autopilot that was programmed was also an issue. So it's like the autopilot problem became the cherry on top. So it was these problems were bogging us down and led to the failure of the second vehicle also. So this was the moment like where they had to go back to the drawing board and multiple things had to be relooked, redesigned and extensively tested till their failure point, just to make sure that we have the right stuff in our design or we have the right product or design in our hands. So soon after this, a number of corrective steps were taken just to overcome the design inadequacies that we saw in the second launch. This involved modifications for a less demanding flight regime and more intensive simulation studies were carried out. Again, the study and simulations are very important when you are designing something that you know for a fact that is going to be experiencing huge and tremendous amount of pressure. After that, specific design changes were included. Modifications to the strap-on motor propulsion design were created. This was done to reduce the maximum thrust at burnout and also reduce the dynamic pressure of the vehicle, and these were implemented in the new version of the ASLV. Now, during when all this redesigning and rework was being done, it was decided to add fins on the core of the vehicle to help with its stability and bring down the demand on control forces. So to increase the stability of the vehicle itself, they decided to add fins on the core stage of the vehicle. And it certainly worked. The fins that they added increased a lot of stability when the vehicle was under spin. In addition to all the structural changes, various software additions were also done to help with the real-time decision making, and the culmination of all these changes, the hard work, the redesigns, the reworks, the testing upon testing, all these things came into reality on the third flight of ASLV, which was dubbed D3 on May 20th of 1992. This was a successful mission. Before we understand the success of ASLV D3, let us understand what the problems were in a bit detail here. In the first two launches, it was established that ASLV was generating around 900 kilonewtons of thrust, and the height to diameter ratio of ASLV was very skewed. It was skewed to a point where it was impacting the motion and function of the vehicle as a whole. What does this mean? Simply put, the vehicle was being very unstable during a flight. It was acting abnormally. It was not normal. Now, as we discussed earlier, not only the vehicle was unstable, the things that were needed to go right in order for the vehicle to be a successful launch were also a long list of things. Because sequential, right? Every event has to go off impeccable timing. There shouldn't be any delay. If one thing misfires, the whole vehicle is lost. So as I discussed earlier, the sequencing has to be right. If one point in a long list of things fails, or one mechanism fails to fire at an appropriate time, it would certainly have a knock-on effect on the whole mission itself. Again, loss of vehicle, loss of payload, mission ended. To put a nail in the coffin, as one says, the systems and the subsystems integrated into the vehicle have to perform flawlessly. And remember, all these things were happening simultaneously at a point in time where the vehicle was experiencing or was under tremendous pressure too. In a nutshell, things were afar from what we were used to with both sounding rockets and SLV. So this was new territory for our scientists. We weren't used to this, or we don't have enough experience in this territory. So we were learning as we were going. Moving on to the third launch of the vehicle itself, that is D3, it was a success. But the interesting thing is, when you go to Wikipedia ASLV page and look at the launch column of it, or the table for it, in the column for D3, it shows the mission as a partial failure. That is simply because the vehicle was carrying a 106 kg stretch Rohini satellite, SRO SSC to those interested, with that as its payload, which was to conduct some scientific experiments, which I forgot, forgive me, but it was nonetheless a stretched Rohini satellite, and the mission was it to carry some certain scientific experiments. But coming back to the issue at hand, due to an anomaly in the imparted spin rate, the satellite was placed in a lower orbit and had only a short lifespan of 2 months, meaning the satellite was injected into the wrong orbit. What was the reason? The anomaly was simply an imparted spin rate which was not anticipated. As a result, low orbit, only the lifespan was 2 months, and as a result of this, the satellite decayed quickly from the orbit itself, burned up in the atmosphere on re-entry. So that is why it is attributed as a partial failure. But remember, when a mission is considered, the placement of the payload is one aspect of the whole launch mission, and the launch sequence itself is a different aspect. Remember this, when we were building ASLV, our entire idea was to build a launch vehicle that acts as a baseline for our future launch vehicle technologies, and for also our desire for space exploration, particularly scientific space exploration. And in that regards, D3 was a critical success. Because let me tell you, what was so successful about, or what was the successful aspect of D3? To put it simply, D3 demonstrated the indigenous expertise available in design, all while showcasing that we were capable of developing and designing complex satellite launch vehicles to carry out complex satellite launch missions. So we were able to demonstrate that to the world itself. So in my book, that is a success. So the success of this mission not only lifted our spirits, it also validated a number of technologies that were employed for the first time, such as the strap-on autonomous stages, a new heat shield, a closed-loop guidance system, a real-time decision-making system, telemetry software packages, and in physical aspects of it and in terms of propulsion, high-energy solid propulsion systems were tested for the first time. So these were developed indigenously. That's the critical aspect of this entire mission. They were tested at this D3 mission. The D3 became a platform or a test bed for all these indigenously developed technologies. Finally, the most important of all these is the successful vertical integration of the vehicle itself. And that, coupled with the ground station network interfaces required for future launch vehicles, was also developed and achieved during this particular period. So when you look at it through, the satellite was placed at a lower orbit, the vehicle performed flawlessly, and it was a testament to the advances that we made in terms of building our own launch vehicles. And like that of SLV 3, ASLV also had its fourth and final launch in the September of 1994, and ASLV D4 met all of the flight and orbital criteria, and it was a complete success. Again, it was carrying a satellite payload, that is the stretched Rohini satellite, which was weighing around 113 kgs, and it was a complete success in terms of both the successful launch system or the performance of launch vehicle flawlessly and the perfect injection of the satellite in its intended orbit. So to give you a little bit of understanding how the development takes place in the minds of scientists, or in our development, in our strive to get a better vehicle out of our existing infrastructure, let me give you a little bit of what were the modifications that ISRO made from D3 to D4. On the launch vehicle side of ASLV, the spin-up system was redesigned to improve the reliability in the view of lower spin rate that was observed during D3 flight. The closed loop guidance system, its algorithm was also modified to meet the critical mission parameters and mission requirements. In addition to that, the onboard software was also subjected to stress testing before being incorporated into the vehicle, just to detect and avoid any computational errors that might be induced due to these extensive circumstances and conditions. These were just the few modifications and changes that were made from D3 to D4, which made it possible that D4 was a complete success, meaning it was a successful mission. To note an interesting point here, all of the ASLV launches took place from Sriharikota, meaning the special launch pad that was built for ASLV specifically, and this was the beginning of our own launch pad, that is Satish Dhawan Space Center, which is in Sriharikota, Andhra Pradesh. And all the vehicles were integrated vertically, which meant that we learned how to do it in a safe, secure, and simple manner. Many of the ground facilities that were built for SLV3 were reused, new structures were built, and with the successful launch of ASLV, and with the culmination of all the things that we have learned during the developmental phase of SLV3 and ASLV, led to ISRO coming out with the PSLV, its workhorse, which we'll be discussing in the next episode. I cannot wait to share the information that I learned during the research for PSLV. I think the role ASLV played was that of validating our competence in design, particularly designing of complex launch systems. ASLV acted as a testbed, that is the backbone that enabled us to prove a lot of technologies that went in future and helped us in realizing our future launch vehicle systems, and also helped us to develop a new class of satellites by way of allowing us to test new technologies both in terms of vehicles and in terms of satellite. Thank you for listening. Hope that you have enjoyed listening to this episode as I enjoyed making this one. This is just the second episode of many more to come in the future, where I'll be exploring launch vehicles of various other space agencies, that is countries, both government and private, through different seasons. This is just season 1. This has been Launch Vehicles season 1 episode 2 of India series. Once again, I thank you from the bottom of my heart. Thank you for subscribing to Akashvata. If you have any more suggestions, I'd love to explore them and present them to you, or do any specific videos pertaining to any specific topic. If you want to see me to do some audio series on some specific topic, please do leave a comment. To do that, please follow me on YouTube and on all major podcasting platforms, and I have a Twitter account too at Akashvarta @AKASHAVAARTHA. Please don't ask me for the spelling. I repeat again, Twitter at AKASHAVAARTHA. You can interact with me there, and I'll try to the best of my knowledge, answer any of your questions you may have regarding the audio series that I am doing or anything that is related to space. I'll be honest with you. If you have any suggestions, please let me know through all of these platforms, either through comments on YouTube or through Twitter, which I'll be gladly to make videos for you and incorporate your suggestions and ideas in my future audio series or videos that I'll be doing. And again, I'm really thankful that I got this opportunity, and I'm happy that I'm sharing this with you. Once again, thank you very much. Please do comment, share, subscribe, and follow on YouTube and Twitter, and I'll be seeing you in the next one. Namaste.